Hello, this is Sadashiv Fadnis, Product Marketing Manager for Rubidium signal generators here at Anritsu. In this video, I'll be talking about generating a chirp using user-defined modulation option in Rubidium. Rubidium supports many standard analog modulation schemes such as AM, FM, PM, and pulse. It is also possible to enable a combination of modulation schemes simultaneously. This video will show how to create a chirp using user-defined modulation option by enabling internal FM and pulse modulations simultaneously. First, I will explain conceptually how a chirp can be generated by enabling FM and pulse modulations simultaneously. We start with pulse modulation. The time during which pulse is on is called pulse width. Pulse also has a repetition interval, which is also called pulse period, as shown here. We set the pulse width equal to the width of the chirp that we would like to generate. We set the pulse period equal to the chirp repetition interval or repetition period. Next, we use a ramp waveform for FM modulation. The start of the ramp is always synchronized with start of the pulse. The period of the ramp is set equal to the pulse width. When we simultaneously enable FM and pulse modulation with synchronized waveforms as they are shown here, we get a chirp. This is my demo setup. The RF output of Rubidium signal generator is connected to MS2090A Anritsu handheld spectrum analyzer. You can see that I have connected Rubidium's FM and pulse baseband outputs to an oscilloscope so that we can see the baseband waveforms being used for internal modulation. The Ethernet ports of Rubidium, MS2090A, and oscilloscope are all connected to my laptop through an Ethernet switch. This enables me to run remote GUIs for each instrument on the laptop so that I can control, configure, and display Rubidium's waveforms or RF output spectrum on the laptop as needed. Here is my laptop screen with 3 remote GUIs. This is the Rubidium GUI. It pretty much mirrors the GUI on the front panel of the Rubidium. This is the MS2090A remote GUI. It also mirrors the GUI on the MS2090 instrument itself. With these two GUIs, we have full capability to configure settings on each of the instruments. This is oscilloscope GUI. It is not fully functional GUI in the sense that we can't make configuration settings on this GUI. All we are doing here is accessing a page published by oscilloscope located at its IP address. The oscilloscope has a VXI11 server, and a snapshot of oscilloscope's display is published on the page every 10 milliseconds or so. This GUI on my screen here accesses that page. We are going to access the page whenever we want to see Rubidium's waveforms. So let's come back to the Rubidium GUI. We will start with configuring the pulse modulation as I had described in my portion of the video where I was explaining conceptually how we can generate a chirp. So we'll start with the pulse modulation, but before that we'll set the output frequency of Rubidium to 10 GHz and level to 0 dBm. and we can see the output here on the 2090 spectrum analyzer at 10 gigahertz and 0 dBm. So having set the frequency and the level, we'll move on to the modulation section. In the modulations, let's start with the pulse. We will set the pulse period to 1 millisecond, which is 1 kilohertz repetition frequency, and we'll set the count to 1. Pulse count to 1 essentially means that there will be one pulse every PRF period, and then we will set the pulse width. When there is only one pulse, the delay does not matter. It will always start at the start of the pulse. The delay will be essentially 0, so this setting does not matter. The pulse width, this is the pulse width, and we will set it to 500 microseconds, which means this will be a pulse pattern with 50% duty cycle. So we'll set it to 50%, and then we will go back and we will enable the pulse modulation. And when you enable the pulse modulation, let's go back to the oscilloscope and check what waveform do we see. There you go. So you have your pulse with 50% duty cycle. This is 500 microseconds of the pulse width or the on period, and then overall is 1 millisecond. The pulse repetition period is 1 millisecond or 1000 microseconds. Okay, so having configured the pulse, the next thing is we will move on to the frequency. We will choose the waveform. We'll choose the positive waveform, positive ramp, and as I said, if you go back to this oscilloscope screen again, the idea was to set the ramp, the period of the ramp equal to the pulse width, right? So the pulse width here is 500 microseconds. So reciprocal of that 500 microseconds is 2 kilohertz. So the rate is 2 kilohertz. The rate of the positive ramp is going to be 2 kilohertz, so that it completes one ramp within this on period, right? So we'll set the rate to 2 kilohertz. We have set the rate to 2 kilohertz. The deviation, will set the deviation to say 1 megahertz for now. So let's set it to 1 megahertz. So we'll set the deviation to 1 megahertz positive ramp, and then we'll enable it. And when we enable it, let's look at whether we are able to see it on the scope. So we'll update this, take a snapshot, and there you go. So you have a ramp generated for FM modulation, and as you can see, it is synchronized with the start of the pulse. It is always synchronized with the start of the pulse. Now this is the off period and this is on again, right? So what happens is whenever the pulse is on, the carrier is going to get FM modulated by this ramp. So this will be a chirp during this on period. Off period, the RF is off, right? Now let's see whether we see that on the spectrum analyzer, whether we see this FM modulation happening on MS-2090. And there you see the FM modulation. I think let's adjust the span so that it becomes, right now the span is too large because our deviation, remember our deviation is 1 megahertz. So in order to see this, we are going to reduce the span to 10 megahertz, and there you go. You can see more clearly now the swing of the FM modulated signal, right? And in order to see more clearly what the total plus minus span is of the plus minus deviation is, what we will do is we will choose the trace type and we'll do a max hold. And when you do the max hold, you can see this is the 10 gigahertz center frequency, and it's swinging on either side of 10 gigahertz by 1 megahertz plus minus 1, because we set the deviation to 1 megahertz, right? So whenever during this on period the RF carrier is to swing from 10 gigahertz minus 1 megahertz to 10 gigahertz plus 1 megahertz, and that's basically our chirp, right? Now if you want to increase the deviation, let's say I increase this deviation, if you want higher deviation, let's say you set it to 2 megahertz, and so 2 megahertz, okay, and then we go back to the spectrum analyzer, it will show you plus minus 2 megahertz swing here, right? And all that is happening within this on period, so you get a chirp of plus minus 2 megahertz deviation. Now let's say you don't want this 50% duty cycle, right? You want a symmetric duty cycle. You can do that too, but always remember that you have to synchronize the ramp on period to the pulse width all the time, right? So it's very important to remember that. So let's go back to the pulse, and that pulse width, let's say instead of 200 microseconds, I'm going to set it to 250 microseconds, right? Okay, so when we set it to 250 microseconds, let's update the display and see what we get. So now we get much smaller pulse width, that means much smaller duty cycle. So you varied the duty cycle of the pulse, but how do we get back our ramp with this 2 megahertz deviation? How do we get back our chirp with 2 megahertz deviation? For that, you have to set this ramp period to this 250 microseconds again. So the reciprocal of 250 microseconds is 4 kilohertz. So you go back and you set the rate to 4 kilohertz, and then let's see what we get on the oscilloscope. There you go. So within this on period you have one full swing of plus minus 2 megahertz, which you can see here. So let's refresh again. Let's go back, trace, clear right, and max hold, and you will see the entire swing, right, of plus minus 2 megahertz here, around 2 gigahertz, right? So around 2 gigahertz you see plus minus. So that's how you get back your deviation even after you change the duty cycle, right? Now what happens if you want to have a larger duty cycle, which means greater on period? Yes, you can do that too, but always remember that your ramp should be adjusted back to the on period. Your ramp period should be adjusted back to the on period. So let's go back again and I'll show you how. Let's say I change this to 800 microseconds. 800 microseconds. Okay, 800 microseconds. Let's go back and let's see what we see on the oscilloscope. There you go. Now your on period is much larger, but you have multiple ramp cycles here, so this ramp needs to be adjusted to this. Ramp period needs to be adjusted to this pulse width period. So let's go back to frequency. The pulse width, as we saw, was 800 microseconds. So the reciprocal of 800 microseconds is 1.25 kilohertz. 1.25 kilohertz. You set that to 1.25 kilohertz, and let's see what we see on the scope. Okay, so now your ramp period is adjusted to the pulse width period, which is 1.25 microseconds, so that you get back your plus minus 2 megahertz deviation of the chirp. But what is happening in the off period? You see this funny little small ramp again, and then back to your original ramp. Don't worry about this ramp, because what signal generator does is it always synchronizes your start of the ramp with the start of the pulse all the time, right? And what happens in the off period, you really don't care about it, because the RF is off during that period, right? Your chirp is off, right? So this is okay. So the most important thing to remember here is always adjust your ramp period to the pulse width, you know. So as long as you can do that, as long as you do that, you get your specified deviation within that chirp. And again, let's go back to this spectrum analyzer and see our trace. Go back to clear right and do another max hold, and you can see that you are getting your original ramp, right? Sorry, you are getting your original deviation plus minus 2 megahertz. So that is how this is how the chirp looks like in the frequency domain. Now what I will do is I'll also show you what it looks like in the time domain. And in order to show that in the time domain, because our oscilloscope's max frequency is rather limited, it's not 10 gigahertz, it's 500 megahertz, and I'm going to, and then because we want to see the chirp in the time domain, what I have to do is I have to go back to the frequency here and then adjust the frequency to the output frequency, Rubidium's output frequency, to a much lower value. And we are going to do that in the next section.